Module 15, the urinary system. Urine formation, step 4, reabsorption of water. The fourth and final step of how the kidneys form urine is the reabsorption of water. I already discussed this process a bit during the discussion of step 2, but water is such an important material in the body that there is a lot more to learn about its control. It has to be carefully balanced so that when you take in too much water, the excess needs to be removed by the kidneys, and if you take in too little water, the kidneys retain what you have. It requires a good bit of regulation. This all-important process has to do with the uniqueness of the interstitial fluid that is deep within the kidneys. It's not like the interstitial fluid in much of the rest of the body. It's more concentrated. Regular interstitial fluid has a solute concentration of about 300 milliosmoles per kilogram. That unit has to do with a measure of solute concentration, so a greater milliosmole per kilogram number means greater concentration of solutes. The blood plasma has about the same concentration too, 300 milliosmoles per kilogram. In the kidney, the concentration of solutes in the cortex is also about 300 milliosmoles per kilogram. But as you move deeper and deeper into the medulla of the kidney, the concentration gets greater and greater. In the innermost part of the medulla, the concentration of solutes reaches 1200 milliosmoles per kilogram. This is mainly due to the presence of urea in the interstitial tissues there. But it's not a bad thing. In fact, it's an important feature of the kidney to help with water reabsorption. Let's first back up a bit and discuss the basics of the control of water reabsorption. Take a look at this nephron. It has a loop of Henle. Remember that only about 10% of all nephrons have loops of Henle. It's these nephrons that are responsible for the concentration of urine via the reabsorption of water. Now, the nephron's renal corpuscle and its proximal tubule are both located in the cortex of the kidney. The loop of Henle travels down into the medulla where the concentration of solutes is so great, and then it comes back into the cortex where they're back to normal. Then the collecting duct goes back deep into the medulla and into a minor calyx. Remember, as you go from the cortex to the medulla, the concentration of solutes continually increases up to 4 times as much as what is in the cortex. So now I can talk about how water is absorbed. Beginning at the descending loop of Henle, the filtrate inside it has a solute concentration similar to interstitial fluid, or 300 milliosmoles per kilogram. Now, the descending loop is permeable to both water and solutes, but here in the cortex there's no movement of material because of similar concentrations of materials. As the loop travels down into the medulla, the interstitial fluid around it becomes greater and greater in concentration of solutes. This will cause water to travel out of the descending loop via osmosis. It will also draw solutes into the loop via diffusion. So the filtrate becomes more and more concentrated as it moves deeper into the medulla. At the bottom of the loop, the concentration of solutes of the filtrate in the loop is equal to the concentration in the medulla, or 1200 milliosmoles per kilogram. Once the water moves out of the loop of Henle, it doesn't remain in the interstitial fluid there for long. It moves to the vasa recta, which is a specific blood vessel located right here. Thus, that water that was in the filtrate is now back in the bloodstream. But now let's follow the filtrate as it moves up the ascending loop of Henle. This portion of the loop is not permeable to water or to solutes. Therefore, the only way that material can move through it is via active transport, which requires energy. So as the filtrate moves up the ascending tube, only 3 materials can be transported out: sodium ions, potassium ions, and chloride ions. All 3 of these ions have carrier molecules that can move them out. When they move out, they also move to the interstitial fluid and then to the vasa recta, re-entering the blood. So when these ions leave the filtrate, the concentration of solutes in the ascending part of the loop of Henle goes down. That's because the water cannot follow the sodium, potassium, or chloride ions out of that impermeable membrane. This situation results in a total solute concentration of about 100 milliosmoles per kilogram. Well, at this point, about the only major solute left in the filtrate is urea. There was some in the filtrate before it moved into the loop of Henle, and more entered it as it descended into the medulla. And that's a good thing. You see, the sodium, potassium, and chloride ions in the filtrate are electrolytes. When they are dissolved in water, they are able to conduct electricity. And the concentration of these ions is a critical component to the health of the body. So you don't want to lose too many of them. But electrolytes easily dissolve in water, so they will follow it as it moves into the body. Therefore, if the thick part of the ascending loop of Henle was not thick, water could not be retained inside it while the electrolytes left. Well, once the filtrate has moved through the loop of Henle, it's in the distal tubule. Remember, it still has a low solute concentration because of the active transport of electrolytes out of the nephron. At this point, whatever happens has to do with the presence of antidiuretic hormone, which is a hormone made by the posterior pituitary gland. When you studied the endocrine system, you learned that the hypothalamus of the brain controls the production of this hormone that is responsible for controlling how much urine is produced by the body. If there's too much water in the blood, then little antidiuretic hormone will be made, so that a lot of urine is produced. If there's too little water in the blood, then lots of antidiuretic hormone will be made and released so that little urine is produced. What lets the endocrine system know when to release this hormone? Well, when you are relatively dehydrated, all the cells in the body shrink up a bit because there's less water in them. And the shrinking of cells in a certain spot of the hypothalamus causes the stimulation of some neurons there. Those neurons have axons that travel to the posterior pituitary gland, which causes those neurons to release antidiuretic hormone. How does this hormone cause more or less urine to be produced? Well, its presence in the kidney makes the distal tubule and collecting duct permeable to water. More antidiuretic hormone, the more permeable these tubules are. Say, for example, you've been working in the yard during the summer, pulling weeds. You've been sweating and breathing heavily for a while as you did your work. Thus, you have a bit of a shortage of water in your body due to the loss in sweat and loss of moisture from your breathing. Your blood has to reabsorb as much water as it can from the nephrons then. Well, to do this, there has to be lots of antidiuretic hormone in the kidney so that when the filtrate makes it to the distal tubule and the solute concentration is low, at about 100 milliosmoles per kilogram, it travels toward the collecting duct down into the medulla. The solute concentration in the medulla's interstitial tissue is very high, so if the distal tubule and collecting duct are permeable to water, what will the water do? It will move out of the tubes and into the interstitial tissue and onto the vasa recta, where it will join the bloodstream. A good supply of antidiuretic hormone in the kidney helps extra water in the filtrate to leave it, so it won't be a part of the urine but will go back into the blood. Thus, the urine will be very concentrated now. What about when the body has too much water? Let's say you love lemonade and your mother just made a pitcher of lemonade just the way you like it, so you have 2 or 3 or 4 glasses of it. Well, lemonade is mostly water, so you've taken in a lot of water into your system. Now, the hypothalamus and posterior pituitary will decrease the amount of antidiuretic hormone released so that the permeability of the distal tubule and collecting duct in the kidney are much less permeable to water. So, as the filtrate moves through those tubes, though water may want to move out where the concentration of solutes is greater, it cannot because it cannot move through the membrane. Therefore, it becomes part of the urine, which will be much more dilute in concentration due to water's presence. So, this amazing design of the nephron helps to control the concentration of both materials and water in the filtrate moving through it. There's the thick part of the ascending limb of the loop of Henle, which is always impermeable to water, but will allow for active transport of electrolytes to be sent back to the blood. And there's another part of the nephron, the distal tubes and collecting ducts, that can have varying permeability to water depending on how much water is present in your body. Antidiuretic hormone will make these tubes more permeable to water as a result of not enough water in the body. And if there's too much water in the body, this hormone will not be sent to the kidney so that water is kept within the filtrate to be expelled as part of the urine.